All right, can you all hear me and see me? Are you guys there? Okay, all right, good. So this is our last lecture before the exam on Friday. And I apologize if I wrote up here, I wrote too small up here, but we have an exam on Friday. So you folks will come at 2 o'clock and I will give you the exam in room S102. It's an in-person exam. I did email you a website with really all the sample exams, the rest of the sample exams for the rest of the course. That was the old website we used to use for our department. And that website does include all of my exams and some other goodies. All right. Chapter 25 is due Wednesday. I only have one or two little more things to talk about in chapter 25, and I'm essentially done. So I will do that today. Now, to get ready for the exam, please study the homework problems. Study how you solve the homework problems. Okay? What techniques did you use to solve the problems? That's what I need you to go over. Okay? Same thing with the in-class problems. What technique did I use to do the in-class problems? You do have practice exam. You have a Unit 2 exam that I sent you the other day. I just give you the link to it. But also I have the online just in case there's a version of the practice text if I were to give it online. That's a good practice too. So you actually have 2 practice exams to work with. Okay. And then on Canvas, I have placed on Canvas for this unit a set of conceptual questions for you to practice on. You have answers. And you have questions on the answers, please ask me. Just email me. Of course, I'll be here Thursday night. No, not here, but I'll be at home Thursday night to answer your questions that you may have before the exam. Okay? So I'm providing all these resources for you. Just hopefully, I just want you to use them. Okay? Any questions regarding the exam? Or concerns?
What chapters is it on?
It's chapters 23 through 25.
Okay.
I'm going to start chapter 26 today. Nothing from chapter 26 will be on exam 2.
Okay.
Okay. Other questions? Typically, for this exam, what I've done in the past, and it should show that on the practice test, is that instead of giving you 4 problems to work on, I will give you, you will see either 5 or 6 problems on the exam, and you will choose 4 out of the problems given to solve. But you got to tell me which ones you want me to grade. Otherwise, I grade the first 4 problems you solve. Okay? Are we okay with that?
Yeah, how do we indicate? Just circle the problem? Or...
Yeah, you can just circle the problem, or you can say grade this. As long as it's clear to me. If you circle it or say grade this, that's enough for me.
Okay.
If you don't say anything, then I don't know. That's when I grade the first 4 problems. Okay. Yeah, any indication that tells me you want to grade, circling it or saying grade is fine. Okay. Other questions? Okay, so my goal today is to finish up chapter 25. I just got a couple of things I want to say. And then I'm going to start on chapter 26. That's on the new unit, unit 3. So unit 2. You mind? Somebody needs to mute themselves. So unit 2 is chapter 23 through 25. Unit 3, chapters 26 through 28. We're going to actually go it's 3 chapters per unit from now on. Okay, every unit from now on is 3 chapters. So unit 3 is 26 to 28, the next one is 29 to 31, and then the next one is 32 to 34. Okay? And so whatever I talk about today on chapter 26 will not be on the exam on Friday. Okay. We did finish
Professor?
off the other day
Sorry.
talking about...
Hey, Professor.
Yes?
Sorry, I just have one more quick question. On that link that you sent us of previous exams, the one that corresponds to the exam that we're going to be having on Friday is the first one, right? The exam 1?
Yes.
Okay, cool. Thank you.
Yeah, you're right. Because I did things a little bit differently then. I mean, I changed things recently. So, yeah, I did the relativity. I did the relativity once we went online. And so, yeah, exam 1 is chapters 20 on that website is 23 through 25.
Thank you.
You're right about that. Okay. We talked about the electric potential for conductors in equilibrium. We said that if you have a conductor that's charged, since the electric field is 0 inside the conductor, the electric potential inside the conductor is constant, and the electrical potential on the surface is also constant. In fact, the surface of a conductor is an equal potential. You can also talk about the electric field in a cavity. If you have a cavity, so if you have a conductor with a hole in it, there's nothing in the hole. This conductor between points A and B here is an equal potential. If I integrate the electric field over any path that connects A and B, I got to get 0 because this point is 0 and that point is 0. So this has to be true over any path I take between A and B. That includes a path that goes through here. Well, in order for this to be 0, this E has to be 0 inside. So the electric field inside a conducting cavity, meaning there's nothing in there, is 0. Now, one more thing I want to say, and again, I'm just talking about applications of the ideas we've talked about in chapter 25. If you charge a conductor, actually, if you charge any material, you can't put charge on it indefinitely. At some point, the electric field will strip electrons from nearby molecules. So let's focus on a conductor like this Van de Graaff that I have here. When I charge this thing, I can put so much charge on here that at some point the electric field will strip the electrons from the air molecules. Now you have ions. You have charged particles that can move around. Now the air can conduct. And so what happened then, the air has broken down. Okay. And any insulator can break down. You can actually have a PVC. If you put enough charge in a PVC, it'll break down and it will conduct. Any material, if you break it down, let me rephrase that. Any material, if you charge it enough, will conduct. The material will break down electrically. For air, the breakdown occurs when the electric field is about 3 million volts per meter, or about 70,000 volts per inch. Now that number depends on how much moisture there is in the air. Okay, for a insulator, the breakdown field will depend on how many impurities are in the material. Okay. So when I use this Van de Graaff, when I used it in my demos and you saw the spark generated, it's because the air was breaking down. That spark that you saw was called a corona discharge. Okay, it was called a corona discharge. Anytime you get zapped electrically by something, that's really what you see. That little streak of light you see is really the discharge. If the arc is about 1 inch long, you're talking about 70,000 volts. If the air is dry, if the air is moist, maybe 20,000. Okay. Let me show you a video. Give you an example of a very nice breakdown in the air. And I got this from YouTube. Now check out the side. This is at a power plant. Oh, I got to make this bigger. Sorry. This is at a power plant. So take a look at the arc that you see, the discharge, and compare it to the people near these structures. So those are the people right here. That gives you an idea. I'll do it one more time. That gives you an idea how big that arc was. Okay, this is a fun video to watch. Okay, here we go. So the last thing I want to talk about in this chapter, I think to me it's an important idea. It's going to help us, I think, to understand a little bit about capacitance and just the materials in the next chapter. Okay, and the next unit is this idea of charge sharing. So imagine I have two spheres, and I'm just going to discuss the problem. I have the complete solution in your notes. I'm going to set up the equations, and then the solution just involves algebra, and you guys can do that, so I'm not going to go through that. That's a simple detail. I'm going to talk about the hard part. So let's say I have two conductors. I have a big conductor. Oops. Forgot something. Okay, let's do this right here. Okay, so I have a big conductor of radius R1. And it's at a potential V1, and it has some charge initially, Q1 initial. I'm going to take a second conductor and I'm going to place it far away from the first one. It's going to be a different size. It's going to have radius R2, potential V2, and of course charge Q2 initial. And this is a conductor, so V2 can be easily written as K Q2 initial over R2. And V1, I'll write it down here, is K Q1 initial over R1. So they're far apart from each other. And the reason why I want to put them far apart from each other is because since they're conductors, the electrons are free to move on them. If I put them too close together, the conductors are going to influence each other. If I bring this conductor real close to this one, then the electrons on here are going to experience a repulsive force with the electrons on here, and they're going to rearrange themselves, giving you a very complicated electric field. And so I'm trying to keep them far apart from each other so they don't influence each other. Or the influence between them is very small. So let's assume they're far apart. And so what happens then if I take a wire, a thin wire, and connect them together? What happens when I take a thin wire and connect them together? I have this at one potential and this at another potential. What happens when I connect them together with the wire? I mean, I have a potential difference between the ends of the wire. What happens when I have a potential difference between the ends of a wire? You just did the multimeter quiz. You should know that. Right? You get electrons to flow. You have electricity, right? That's what some people would say. Okay, you have electrons flowing. You have a potential difference between the two ends of the wires. That means you have an electric field in the wire. That means the electrons will flow in the wire when I make that connection. For how long will the electrons flow? When will the electrons stop flowing? When do you think the electrons will stop flowing?
Is it when the charges are equal?
Not when the charges are equal. That's a good guess.
Sorry, Ryan.
No, you're fine. When the potentials are equal.
Yeah, when the potentials are equal. Because when the potentials are equal, then what's the electric field in here? If the potential
Zero?
It's zero, yeah, because now this thing is at an equal potential. Basically, when that happens, this system is basically one big conductor. When you put the wire between them, now you've created one big conductor. So charge will flow until the electric potential on both spheres is the same. I'm writing a shorthand, sorry. Okay? So the question is, if I know the initial charges and the radii, can I figure out the final potential of the system and the final amount of charge on each one of the spheres? In other words, when these are at the same potential, obviously this is going to have a different amount of charge. That's the only way the potential changes. And this will have a different amount of charge on it. So this equation must be true because they're at the same potential when charge starts flowing. And the electric field then in the wire itself is zero. Out here it's not, right? Out here electric field is not because there's charge here on the outside surface of the conductor. I have two unknowns by one equation. How am I going to figure out what Q1 final and Q2 final is? And how can I calculate V final? I have too many unknowns. Can I get another equation?
I think you can get it from the sum of the charges.
Yeah,
of
why?
them individually
Why do you say that?
before you. Because it's just like what Scott said. Like once you connect them, they're going to have the same charge, but before you connect them, they'll have different charges.
So, even though this will
Or
have a
could
different charge before and after, and this will have a different charge before and after, the sum of the charges won't change, right?
Correct.
So whatever I started with has to be equal to whatever I finish with, because charge is conserved. So with these two equations, then I can solve for Q1 final and Q2 final, because I know what the initial values are. That's just conservation of charge. So once I know Q1 final and Q2 final, I can find V final. Now, that's just algebra. So in your notes, I go through this entire problem. So if you want to know the answers, read your notes. Okay. And I mean, I went to a lot of detail to solve this. So let me just show you. So one of the things I do show you is that when this sphere, if this sphere loses charge delta Q, that sphere will gain that same charge. So whatever this one loses, that one will gain, or vice versa. Okay. So whatever this loses, this will be gained. And this because charge is conserved. So I go through and calculate the final V for the system, the final Qs for the system, delta Qs, and also the electric field on the surface of each conductor. So you should study that. Okay, and I'm going to skip this example with the parallel plane analyzer. We actually did this problem in chapter 23, except we wrote everything in terms of the electric field. It's a kinematics problem, basically. So I'm going to skip this just in the interest of time. And we're really done with chapter 25. But I want to do one more interesting example. And I want to spend 15 minutes on it. Okay. Just a second. I can't find. Let me change this. Okay. So I want to do one simple example. Or I should say interesting example. Maybe it's not simple, but it's interesting. And I normally do this, I normally talk about this when we do the properties of charge lab, but the way we had to structure the lab this semester, I had to wait till now. When we talked about the properties of charge lab, we defined what a dipole was. Two charges that are closely separated. And we actually defined something called the electric dipole moment as P equals Q times L. These are equal but opposite charge. The vector L goes from the negative charge to the positive charge. This idea has useful applications in physics. Now, where does this idea come from? Where is it used? It turns out that if you calculate the electric potential at this point P, due to these two charges, where these distances are much greater than this distance. Okay, so when you're P is basically real far away from these charges. You can write an expression and then do an expansion, like a Taylor series expansion, on the function you get for V. And the first non-zero term that you get will have products of this in it. That's called a dipole term. And that's going to be the largest term in your series. And so you can just focus on that term in the series and then ignore everything else. And subsequent calculations will be very easy mathematically. It's one of the examples why we use this idea. If I had something like this, and I calculate electric potential up there, and then I expanded the electric potential, the dipole term, the Q times L term, would actually be 0. And the next term in the expansion will be non-zero. That's called a quadrupole term. And then you use the quadrupole term to look at the physics of the system. And so we use the expansion of the electric potential, and just look at the first non-zero term, to study a physical system. That's because the math is a little bit easier to deal with in some systems. So we talk about dipole, quadrupoles, octopoles, etc. And we use those to basically, as approximations to the actual problems so that we can actually have something that's easy to work with. Okay? If you go on Canvas, there's a document of this problem completely solved with the expansion. Well, it's this problem. Professor Shakel made that. It's a nice document which goes through all the details of the calculation. You should take a look at it. Okay? So that way you get to see where it comes from. I'm not going to focus on where it comes from, but I want to look at how this is used. Okay? So imagine...
Hey, Professor?
Yeah.
So whether it's being a dipole or a quad pole, is that just indicative of how many point charges you have? So
yeah,
like
the
you had
sum
two
is
and
0.
It's a dipole. Okay.
I'm sorry I interrupted. But yeah, the sum of the charges ends up being 0. So for a quadrupole, because minus q plus q here, or I could do this too. This is a quadrupole. There's basically four charges of magnitude q.
I see what you're saying. So it's not like necessarily the point charges, but like the charge or the factor of q that each charge has.
Yeah.
Okay, thank you.
And it's a nice problem. That problem is nice just because you get to learn how to practice with expansion of functions. Okay. Anyway, then once we have this, once we know where this comes from, we can think of what happens to a dipole in the field. Suppose we have an electric dipole like this along the x-axis, and we place it in a uniform field. So let's say this is a uniform field, meaning everywhere along here on my board, E is the same. What's the force on that dipole? Well, I got to draw a free body diagram, right? That's the first thing you were thinking of, right? That I should draw a free body diagram. So the force on this guy is Q times E, and the force on this guy is minus Q times E. So what's the sum of the forces? Zero. So the sum of the forces is 0. So the electric force on a dipole in a uniform electric field is 0. Okay? It really doesn't matter what the orientation is. What about if the field is not uniform? Let's let the magnitude of this, we'll call it delta x. Okay. What is the field? I'm sorry, what is the force on this thing if the electric field is non-uniform? So what I want to say here, the field is E sub x. And the field here is E at x plus delta x. And so if I sum forces, the force on this guy is going to be Q times E at x plus delta x. And by the way, just to make life easy for us, let's assume that the dipole's along the x direction and the electric field's along the x direction. Otherwise, the problem becomes kind of complicated. So that's the force on this guy. The force on this guy is in the opposite direction, but it's minus Q times E at x. So that's the total force. It's not zero because the field here is different from the field here. Let me factor out a Q. And there's two approaches to this. I'm going to show you two different approaches to get my final answer. So the field is non-uniform. Here's E sub x, E at x, and here's E at x plus delta x. I got rid of the arrowhead because the field just points along the x direction and the dipole's along the x direction. Let me multiply numerator and denominator by delta x. I can do that, right? Because all I'm doing is multiplying by 1. What is this equal to? Isn't this a dipole moment? The answer is yes. So this is the dipole moment. And now delta x is small. In fact, what happens to this and the limit as delta x goes to 0? What is that called? The thing in the brackets, and the limit as delta x goes to 0, what is that?
Is that infinity or an improper limit?
First thing you learn in calculus, in Calc 1, what was it? What was it? What's the definition of derivative? Isn't the definition
Slope of the tangent line?
I'm sorry?
Slope of the tangent line?
Yeah, but isn't it this? Isn't it the derivative? It's called a difference quotient. That's the first thing you learn in calculus. Well, beside limit stuff. Go back to your calculus book if you don't remember. But this is the definition of a derivative. Okay, so then this is just P sub x, I should put P sub x times dE over dx. And really E is in the x direction, okay? So the force on a dipole in a non-uniform field is is P sub x times dE sub x dx. I can do this a different way. Maybe that wasn't satisfying to you. Maybe you didn't like that. Let's do this a different way. We had this, And again, delta x is very small, right, for a dipole. Remember, delta x is basically the magnitude of this vector. Couldn't I, using my knowledge of math, Calc 2, expand this using a Taylor series? If I expand this in a Taylor series, just this part, oops, I have it backwards. Sorry. So let me expand this term in a Taylor series. It's going to be, and I'm going to expand it about the point x. And I'm just going to keep the first term with the first derivative term, because the other terms are going to be really small. The term with x squared, the term with delta x squared is going to be really small because delta x is small. So what do I get? Well, this cancels. And I get q delta x e prime sub x. Remember, this is an expansion using the Taylor series, and so this is a derivative. Okay, so again, I get the same thing. Now, I'm assuming here in my derivation P is along the x direction, and the electric field is along the x direction. If the electric field were not along the x direction, then when I expand this thing in 3 dimensions, I have to use a Taylor series that you would learn in Calc 3. I'm not going to do that here. Okay, but so the general equation is much more complicated. Okay, but at least it gives you an idea of what the force on a dipole in a non-uniform field is, at least for one that's oriented along the x direction. Okay. Let me ask another question. Suppose we have an electric field. I'm going to draw the electric field first. Let's pretend the field is uniform. And here's my dipole, oriented like this. It's at an angle. If I put that dipole in that field, what's going to happen to the dipole? Just imagine two masses connected by a rod. What's going to happen to that dipole in the field?
Rotate?
It's going to want to rotate, right? It's going to want to do this. Okay, so this is going to want to rotate clockwise. So rotation means there's a torque on it. Can we derive an equation for the torque on this dipole? Well, yeah, I'm going to calculate the torque about this point, the center of it. Remember, torque is R cross F. So this is one of my R's. This R points in the opposite direction. This R is just half that vector. And so the torque is going to be L over 2 cross QE by R cross F plus negative L over 2 cross minus Q times E. These minus signs cancel. You get the same term. You get Q times L cross E is P cross E. So this is the torque on a dipole in a uniform field. The equation is much more complicated in a non-uniform field. We will not discuss that. Okay? So this is the torque on a dipole in a uniform field. Now, because the electric field is conservative, then when this thing rotates, energy is going to be stored on the dipole. So let's calculate that. What is the energy stored by dipole in the field? So in order for me to do this, first of all, the torque again is P cross E. I want to calculate the work done by the field on the dipole. In chapter 10 of your book, and you're going to have to go back to this, you might not remember it. It says that the work done by a torque is given by this, where this is the angle through which it's rotated. The dipole is rotated, okay, or or whatever is rotated. Okay, the torque, the magnitude of torque times d theta. If you integrate this, that'll give you the work done by the field. Well, the magnitude of that is P times E times sine of theta. That's the magnitude of a cross product. And this is going to be minus delta U. The work done by the field is always minus delta U. So then delta U, U final minus U initial, is minus the integral from theta initial to theta final Now, before I go on, I have a problem here. And it's because of the way I'm integrating. What's happening to theta in that field?
Getting smaller?
It's getting smaller. So d theta is really less than 0, right? I'm integrating in a direction where d theta is less than 0. Isn't that true? Because it's getting smaller. So I actually got to put another minus sign. Here. So this minus sign and that minus sign cancel. What's the integral of sine?
Negative cosine.
Okay. So I'm going
Right.
to get u final. Okay, so I'm going to let theta initial be 90 degrees. What's cosine of 90?
1,
What?
0.
It's 0, right?
Yeah.
And so I'm going to define u to be 0 when theta is 90. And so I'm going to say u is minus p e cosine of theta. Or u initial is minus p e cosine of theta. And that's going to be true in general And so U is minus P E cosine of theta. But I can write that as a dot product. And so I can say U is minus P dot E. So that's the energy stored. On a dipole in a uniform field.
U is the potential energy, right?
Correct. That's the potential
Okay.
energy. So there's some, just some examples of applying the ideas in this chapter, but I applied it to a dipole. And what I've done are simple cases. You can get more complicated by making the field non-uniform, etc. But I don't want to do that. Okay, but just some simple applications of the ideas in this chapter. Okay. I'm going to stop here for this chapter. I'm going to begin the new chapter. I just got to find my cursor. So I want to start chapter 26. So the rest of the time we're going to be focusing today on is chapter 26. Okay, and it's the third unit. Now we're going to start moving away from electrostatics and start looking at the motion of charge in a wire. That's not going to really occur in this chapter, but you'll see it in 27 and 28 and when we start looking at circuits. And you're already doing that in the lab. So I need to talk about what is a capacitor and define capacitance before we can do anything with the concept. And you're going to say, well, what is this idea used for? Well, it helps us to understand something called a capacitor, which is a very practical element of a circuit. For example, every time you push a button on your keyboard, you're really changing the value of a capacitance. When you're using the intermittent windshield wipers on your car, you're actually using a capacitor. Every time you change the timing on your intermittent washer, you're changing the value of a capacitance. A defibrillator uses a capacitance. Anything in a circuit that involves timing will involve capacitors. Capacitors are devices that store energy, but they have a lot of applications. So let me start by saying that if you do an experiment, and it's really hard to demonstrate that here. I've tried it many times, but I haven't been able to find a good way to demonstrate it. You can perform an experiment and charge a conductor. Just a single conductor. And what you'll find is the amount of charge that you can put on the conductor really depends on the size and the shape of the conductor and the electrical potential of the conductor. Okay? And what we want to do is define a quantity that relates the potential to the amount of charge and energy stored by a local field. We want to define a quantity that relates the amount of charge, another way to look at it, on a single conductor, to the potential applied to it. And so we're going to define capacitance with the letter C as the ratio of the charge over the potential of the capacitor. So if we're dealing with a single capacitor, then it's Q over V. And what this represents is how much charge do I have to place on the conductor to increase the voltage by a single volt on the conductor. Now there's another one called mutual capacitance. Again, it's how much charge I have to place on two oppositely charged conductors, two oppositely charged adjacent conductors, so I can raise the potential difference by 1 volt. Our focus in this chapter is to look at mutual capacitance, even though our book doesn't use the term mutual capacitance. Our book just says capacitance. And when we talk about capacitance in our book, we're referring to either one of these. We're either talking about two adjacent conductors or a single conductor. Now, when we talk about a single conductor, when we use this definition, we're assuming there's a very large conductor infinitely far away. Okay, and I'll do an example of that with a sphere later. All right. Capacitance is a little more complicated than this, but I'm going to use a common definition of capacitance, and really this is our common definition of capacitance. Okay, we're going to look at a pair of oppositely charged conductors, and this is the definition for the capacitance of a pair of oppositely charged conductors. Now, if we have more than two conductors, you can define capacitance also, but life gets more complicated. Let's not worry about that here in the case of 3 conductors or more. So what happens when a battery is connected to a parallel plate capacitor? There's 2 large plates. Okay, so I'll put a plate here and a plate here. They don't have to be infinitely big. To a good approximation, if the area of the capacitor is much greater, the dimensions of the capacitor is much greater than the plate separation, we can just say it's infinitely sized capacitor, okay? Because the equation for electric field works well. I'm not going to use a schematic diagram for a battery right now. We will do that soon. So let's say I make this connection. And I make this connection. What happens when I make this connection? Well, charge will flow onto this plate until the potential on this plate equals the potential of this side of the battery. So when a negative charge goes into the positive terminal of the battery, leaving an excess of positive charge, that's going to draw electrons up onto this plate. Okay, I'm hearing a lot of feedback. I'm not sure where that came from. You guys hear me okay?
Yeah, we can hear you.
Okay, I just all of a sudden heard a really bad feedback. Okay. So when the first charge goes here, then you'll see a charge here too, right? When this gets positively charged, then that's going to become negatively charged. And charge will flow in these wires until the potential on this plate equals the potential on this side of the battery. And as a result, you'll have plus Q here M minus Q here. And you'll have a delta V across here. And you'll have an electric field that points from left to right, according to my picture. Okay, let's say the plates are separated by a distance d. And the electric field is E. And I want to use my definition of capacitance to calculate the capacitance of that system. So now, capacitance is always defined as a positive number. So we always use absolute values. So the total charge on it, or let's look at it. Let's do it this way. Okay. And then C is called our capacitance. This is in coulombs per volt. The unit for capacitance is named after Michael Faraday, coulombs per volt. Let me check the chat real quick. Oh. If you write this as, if you write volts as joules per coulomb, then this is also coulombs squared per joule. That's also a farad. And a farad is actually a pretty big unit because most capacitors are the value of the capacitance is very small. Okay? So typically capacitor values are in microfarads or picofarads. Okay? And you'll see them quoted like that. So I'm going to give you an examples of what capacitors, practical capacitors look like. So here's one. There's just a canister. And here's another. This is a big one. This one is 65 microfarads. And you can put up to 2,000 volts on here. If you charge this up and it discharges through you, you're pretty much dead. This thing will kill you. So to keep myself safe, I've actually shorted the two terminals on the capacitor. One of the things about capacitors is you have to be very careful in working with them. The big ones can easily kill you. So this is one that can kill you. This is one that can hurt you a lot. Again, they're shorted. The terminals are shorted. Your air conditioning system has a capacitor in it. Your central air. The first thing that goes bad when your central air goes bad is the capacitor, which costs like $20, $30. Although when you call someone in to repair it, they charge like $300 or $400. Okay. So here's the inside of a capacitor. Just basically they're just two parallel plates. I'll bring it up closer. They're just two parallel plates. They're just wound together. So there's long sheets of aluminum with a dielectric in the middle, with an insulator in the middle. Okay. The plates can be separated by air, or they can be separated by an insulator. Air's an insulator. Okay, so these are just long sheets. They can store energy. I try to not say they store charge because the total charge on the two plates is 0. These are, I don't know if you can see them. These are capacitors we use in the labs for students, so the students learn how they work. These are the two plates of the capacitor. Okay. These don't have any practical uses other than to learn how to use them. These do. These are practical. Okay. So let's say we connect the battery. The plates get fully charged. What's the field between the plates? Each plate produces a field. The field due to the positive one looks like this. The field due to the negative one, oh, let me put the arrow here. The field due to the negative one and they're the same plate, they're just opposite charges, so the electric field produced by each one of them is the same. Each one produces an electric field. Again, we can use Gauss's law, but I'm not going to do that. Each plate produces that for an electric field. But what's the electric field out here? These arrows are equal but opposite. The field out here is 0. These two arrows are equal but opposite. The field out here is 0. But the field here is going to be the sum of the two. And so the total field between the plates is sigma over epsilon naught. Okay? So the total field between the plates is sigma over epsilon naught. Now, what about the potential difference? What about the potential difference between the plate? Well, since the field is uniform, the electrical potential between the plates is just E times D. The gradient is constant. And so delta V, the magnitude of delta V, is sigma over epsilon naught times D. But sigma is the charge per unit area. And so now we know delta V, we can calculate the capacitance. So that's the capacitance of two parallel plates. So capacitance is one of three quantities we're going to learn this semester that depends on geometry. Resistance is the other one, and then at the end of the semester we're going to talk about inductance. They all depend on the geometry of the system. So the capacitance is epsilon naught A over epsilon naught A over D. We're assuming that the dimensions of the plates are much, much greater than D, so that we can use the approximation that the field is given by this expression. Okay, this is only valid if the dimensions of A are much, much bigger than D. So if I were to use this in the lab, if I had my students use this in the lab, To make sure that the plate separation is small, what I do is I put like little spacers. I don't know if you can see the spacers in there. There's white little circles. They're really thin compared to the dimensions of the plate. And so this acts like a parallel plate capacitor essentially. And I have a device called a capacitance meter. Or I had one, disappeared. I had a special device. Oh, here it is. So this device will allow me to measure capacitance. And all I need to do make simple electrical connections. Your multimeter can measure capacitance too. So this device is a little bit more accurate. Okay. Something's not right here. Okay, it's reading 1 nanofarad for the capacitance of this guy. Okay, 1 nanofarad. If I want to scale this up to a 10 to the 9th, imagine I gotta make this bigger by a billion times. Just imagine the size of the plate if I wanted 1 farad. Okay. All right. Questions? Let's ask a conceptual question. Suppose we charge the capacitor with a battery, like I did here. There's 2 plates. We charge it with a battery. And what happens to the electric field, the electrical potential difference, Q and C, if I, for fun, just increase the plate separation? So imagine I did an experiment with a capacitor that looks like this. I have it connected to a battery and I just increase the plate separation. Again, this is a device we use in the lab. What happens if I do this while it's connected to the battery?
Wouldn't the field get smaller?
Ah, okay. Why does it get smaller?
Because the capacitance, I think, would be smaller because D is getting bigger.
Okay, D is getting bigger. How do you see that from here, though? How do you see the relationship between E and D here?
I was talking about C. Sorry, I misspoke and said the field.
Right, right. But you said the capacitance is getting smaller and E is getting smaller. But how do you see that relationship from this equation? Are you looking at it from this equation?
I was looking at the C.
I'm sorry, I didn't hear you.
Well, D and E would both be getting bigger if you increase D.
All right, this is getting bigger. This stays the same.
Oh, so then E would be smaller.
Yeah. Right? Okay, so E decreases. I'll use arrows. And delta V stays constant because it's connected to the battery, right? A battery is a device that maintains the potential difference between its plates, between its terminals. What about Q? What about the charge in the capacitor? Well, if this gets smaller, this stays the same. Doesn't this have to get smaller?
Yeah.
Okay.
Wait.
Or another way to look at it is this way.
I'm gonna get.
We said that this gets smaller, right?
Mhm.
Then this has to get smaller. The charge density decreases. Okay, so we can answer that. I like these these questions because it helps us to remember the material from the second unit. Now, while it's charged, we remove the battery. Let's answer the questions again. Let's assume there's no charge that leaks into the atmosphere. Okay, now what happens? You can do the easiest one first. What happens to C if I increase the plate separation?
It gets smaller.
Smaller. That's not going to change, right? I mean, because C only depends on geometry. Doesn't matter what I do to the whether the battery is connected or not. That has nothing to do with the geometry. Okay, now what else? What else can we answer? What can we say about Q?
Wouldn't Q go down because you took out the battery?
Where's the charge going to go? Where's the charge going?
I don't know.
It has nowhere to go, right?
Yeah. So then Q would stay the same.
That's right. What about the electric field? Let's go back to this equation. If this stays the
Then
same,
it would stay the same.
yeah. You know, we're assuming ideal conditions, okay? What about delta V? What happens to delta V?
Would that also be the same?
Well, let's see. Let's take a look at this equation.
Well, yeah, because E's the same. D isn't changing either because you just took the battery.
We're increasing D, right?
Oh, still? Oh,
yeah,
okay.
yeah. That's what we're doing in part. The second
Okay, I
part.
didn't see that we were also pulling with the part. Okay, so then it would increase.
Increase. Right, and that makes sense because if we increase the plate separation, this gets smaller, this gets the same, this has to get bigger. Now wait a minute, how does V get bigger? Delta V is the energy per unit charge, right? That means there's more energy being stored. Where's the energy coming from when I increase the plate separation? Where's it coming from?
Is it coming from the work?
Yeah, it comes from the work being done on the systems. Something is doing work on the system to increase the plate separation. And so energy is being stored in the system, and the energy is being increased. So when you did the electrophorus lab, and you charged the electrophorus, if you compared the results, let's say you look at the spark generated when the separation was like this, as opposed to when the separation was maybe twice as much, you would find that the spark would be bigger, by touch, if you touch it. It's because you've done more work. You've actually done more work in lifting that up. Now, it's harder to see that in the setup we have. You guys had to do at home, but when we do the lab on campus, you can see the difference. Okay. So you're going to relate this to the electrophorus. So we can calculate capacitance for a lot of different geometries. Let me do a simple one, and then I'll do a harder one. And by the way, if you look in an engineering book, these are tabulated. If you look up, or you can go online, what is the capacitance for spherical, two spheres that are concentric? You can find that right away. These are all tabulated. Of course, you want to know how to calculate them, right? So let me do one that's not in your notes. Let's say I have a conducting sphere with total charge Q and radius R. What's the potential on the surface? Well, V is going to be K Q over R. Let's assume we have a second sphere that's concentric with the first one, but the second one has an infinite radius. And it has charge minus Q on it. This is what will allow us to calculate what's called a self-capacitance. I want to find the capacitance for this thing. So imagine the second conductor is infinitely large. So V for the infinitely large one is 0. I want to calculate C. It's just R over K, or 4 pi epsilon naught R. That's the capacitance of a conducting sphere. Okay, that's a simple one. Of course, depending on the geometry, these calculations can be very difficult. That's a simple one. Now, last week, I talked about two oppositely charged concentric conducting cylindrical shells. Although I made their radii A and B. So I did this problem last week, although I labeled the radii differently. I don't know why I did that. And I'm just going to write down the equation for the potential difference. the magnitude of the potential difference between these two. Okay? I derived this last Tuesday. And I said, if you know this potential difference, you can solve for lambda. That's what I talked about last week. But I want to calculate the capacitance. Now, I have a problem with this because if these things are charged and they're infinitely long, they're going to have an infinite amount of charge. So we can't calculate the capacitance. We have to calculate the capacitance per unit charge of this system. And so we got to calculate lambda over delta V, the absolute value. Okay, so using this that I derived last week, I get this is the capacitance for two concentric cylindrical shells. Basically two concentric wires. Okay, two wires, one inside the other. I mean, that's really the capacitance. And it becomes an important thing when you're studying small signals. Because that capacitance will somehow tie the outer conductor to the inner conductor, and that can cause problems. Okay, so there's a lot of different kind of calculations you can do for various geometries. So this would represent really the capacitance of two what's called coaxial wires. And that knowledge of that capacitance is very important if you're looking at small signals. Okay, I'm going to stop here. And I'm going to continue after lunch. So let's take a break until about 12:50. We'll meet at 12:50, okay? I'm going to go eat lunch. Hopefully you go eat lunch also. I'll see you in a bit.
Recording stopped.